Hello, everybody. Good afternoon. My name is Valerio Setti, and today I'm going to present you another talk about security, but in this case is Zephyr and its security cryptographic features. Starting from a short introduction, I work for Baylibre. I know you know the company by now, but in case not, this is an open source consultancy company based a few kilometers from here, so in the Nice area, which is specialized in all the things related to embedded devices, so Linux kernel, Yocto, McuBoot, Zephyr, of course, and more recently also the C compiler and toolchains. I joined the company in 2022, and since then I have been contributing mostly to Mbed TLS, but also Zephyr, so that now I am part of the Zephyr security working group committee and the Zephyr TSC. When we talk about real constrained embedded devices, so like microcontrollers, I'm sure you know that there are several options available on the market, open source ones. Here I just listed a few of them. The laser pointer is not that great. And Zephyr is among these, and it's owned by the Linux Foundation. Speaking of growth of the project, as shown by this graph, you can see that in the last decade, so since the project's beginning, it has been continuously growing in terms of commits per year, as well as unique contributors. This brings us to the current state where you basically can find support for most, if not all, the available 32 and 64 bits platform on the market, and more than 700 boards, which makes it extremely easy to start playing with that. So if you haven't tried it yet, I strongly suggest to give it a try because it's super easy. There are some products at least already on the market using Zephyr. I just left the link here in case you're curious. The reason for the success of this OS is that it's not only brings you a full feature kernel, which you might have, for example, also with FreeRTOS, just to make an example, but it also comes with a high number of subsystems and modules that brings you a lot of functionality directly out of the box. And crypto is, of course, one of these. The development workflow is, I would say, pretty close to what you would have with an embedded Linux board. So for all the module and subsystems that I mentioned before, but also for the kernel, you can configure and enable, disable single things using a kconfig file. Then you'll have your device tree to describe your hardware. So the end developer only really need to think on developing his own app. The build system is a bit different compared to the Linux kernel because it's a CMake based, and there is a bit of Python scripting. The reason for that is that it performs some checks, but it also automatically generate some source files which are included into the build. The reason for this is that we're talking about really constrained devices. So everything, like the device tree, has to be resolved at build time, not runtime. Having such powerful real-time OS means that IoT is a great application for it. But when we talk about IoT, security is an important feature. So I'll go through some of the subsystems which are requiring crypto support. So you'll find support, for example, for Bluetooth Low Energy, Wi-Fi, and more recently also IoT-specific protocols such as Thread, supported by Open Thread project, and Matter, which require you to support cryptographic, to have cryptographic support somehow in order to have key exchanges, authentication, data encryption, etc. You will also find TLS socket. Doesn't matter if it's wireless or wired, you can have it. And in this case, you also have to handle certificates and again, key exchanges, encryption, decryption, because you would like to connect to a server or you want your device to act like a server. You'll have JWT, JSON Web Token, for client authentication. Or you can also require crypto support for hardening your device. For example, you might want a real random number generator able to generate a large amount of random data. Reason might be you want your device to really behave in a non-predictable way. Usually devices, microcontrollers nowadays comes with some sort of hardware random generator, but it only can provide you a limited amount of data per unit of time. So in case you want to generate larger buffer, that's not good. So you can apply cryptographic magic on top of that to get a larger buffer and use the hardware thing as a seed for that. You will also find a bootloader, which is McuBoot in case of Zephyr, which is used to verify. Actually, it can also decrypt, but for microcontroller, most of the time it's just verify the signatures of the following images before just jumping into them. This clearly is interesting in case you're looking for OTA update, which is possible in Zephyr. You will find secure storage. We saw that there's protocol requirement, TLS, etc., that have sensible material like credentials that needs to be stored somewhere securely, also at rest. And that's where secure storage comes into play. You will also find some remote management tool which have some flash feature, like to verify that the integrity of your flash or part of it is still okay using hash algorithm. Well, all of these means that there is some requirement for a crypto provider, right? So first thing first, speaking of interface for this crypto support, the project recently moved toward adoption of a unified and a single interface for that, named PSA Crypto APIs, where PSA stands for Platform Security Architecture. This is a standard who has been designed by ARM. Actually, the standard defines more than just crypto. It also defines secure storage, attestation, and firmware updates, for example. So what about in practice? Who provides crypto support in Zephyr? Well, nowadays you basically have two options depending on the hardware you're running on. You can either go full software with Mbed TLS or rely on trusted firmware. In the first case, as I said, you're relying on Mbed TLS to provide you everything because Mbed TLS is a full TLS stack library able to provide higher layers with TLS X509 for certificates, as well as the crypto support for that. Just a small notice that crypto support can be provided in two flavors, PSA interface, of course, as well as the legacy ones, which, by the way, is under the process of being removed. The pro of this approach is that, yeah, it's software. See, you can build it for all the platforms that we saw at the beginning. But there are consequences. The main is that it does not support out of the box too many optimization, especially for embedded CPUs, and too many algorithms. And it does not support the hardware accelerators, which nowadays, as for the random number generators, we find in some CPUs, like for AES or other things. There's a few other issues also related to credentials, because during execution, credentials are on RAM. So if your application has some bug that can be exploited to retrieve some data on the RAM, the attacker can just dump part of it, including the credentials, which is not great. And data by default is not securely stored at rest. It's up to the end developer to do that. For this reason, secure storage, as we saw before, has been introduced in Zephyr to overcome this limitation. This brings us to the second solution, which is the most secure one. And it's the one based on trusted firmware RAM. To be noted that this is only available on CPU implementing the ARMv8 or 8.1 architectures, which, as you know, they implement the ARM trust zone. In case you don't know, the trust zone introduces a new state for the CPUs so that we're not just dealing with execution privileges, privileged or unprivileged, but we are also introducing an orthogonal configuration, like you can also jump from secure to non-secure. Of course, the Zephyr application will be, in blue here, on the non-secure side. And whenever it needs to perform any cryptographic operations, it calls into the secure side, where TFM is. And here, there is the transition from non-secure to secure. Some magic is done here to provide the result for the cryptographic operation, and the result is returned back to the non-secure side. On the TFM side, Mbed TLS is still used under the hood, the crypto part, of course, the lower layers, to provide the cryptographic support for that. But the asterisk here highlights the fact that it's not the stock version of Mbed TLS, because TFM team applies a few patches on top of it to add support for some hardware accelerators, yeah, especially the harm ones, like the crypto cells. The other block here, it's meant to highlight that the fact that TFM does not only implement crypto, but it implements the full feature, the full PSA API interface. So you also have secure storage, attestation, firmware update, and status. And speaking about the future work, on the Zephyr side, we'll continue the transition, which has almost be completed toward the adoption of PSA crypto API as a single interface for crypto operations. And we'll continue working on refactoring and improving the integration of Mbed TLS inside Zephyr. Whereas on the Mbed TLS project, there is a major release expected by September this year, where there's going to be, among other things, a repository split, so splitting the higher layers, TLS and X509, compared to the crypto ones. And on the latter, there will be a removal, as I mentioned before, of the legacy crypto interface. After that release, we'll likely also focus on the support for hardware accelerators, somehow out of the box. I don't think there's anything defined clearly yet. But it will help in both scenarios, both in TFM, because you can take advantage of that, of your hardware accelerator, but also in case you're just relying on Mbed TLS as a single library. It won't be the best secure, maybe, but at least you can speed up computations. Yeah, that's it. Thank you for your attention.